pop. All right. So section 2-1, number what?
1, letter C.
Oh, okay. So if you graph it, what did I ask you here? If P is a point on the graph of V, find the slope of secant, blah, blah. Estimate the slope by averaging the slopes of 2 secants lines. So, if you were curious, a couple things, let me build up to that question. If you wanted to know the slope of this line right there, one way you could do it is to get a secant line here, right? Is that the right slope that I want? No. But, I mean, one way, then we could make that point get closer to it, right? But I can take that slope of that secant line, and then on the other side, I can take the slope of that secant line and average them together. It kind of makes sense. If I wanted to know the slope at this point, I can actually get the slopes of 2 secant lines and average those out. Does that kind of make sense? Or, more directly, you could just take the slope between those 2 other points. If they're equidistant on both sides, that's also a good estimate of the slope. Does that make sense? Let me zoom in here a little bit. So if I want to know the slope there, I can take a point on this side and a point on that side. Slope between those would be a good estimate of the slope at that point. Does that make sense? Okay, cool. But in this problem, they said, first they say estimate the slope by taking the average of 2 secant lines. And that's what they mean here. Take 2 secant lines and average them. All right, good. That's number 1. Okay. Blah, blah, blah. And then let's see. Use a graph of the function to estimate the slope of the tangent line of P. So if I ask you to estimate the slope just by my ugly graph here, says 1, 2, 3. How would you do that? I mean, your estimate could be, I don't know. I mean, how would you even try to do that? So obviously they mean to graph this bad boy. One way you could do it is basically, you could just look. You could just look to see, like here it'd be about 0, right? And then a slope of 1 would mean that it would go down 1 over 1. Draw the line in there and see what it would do. So if you can graph this by hand, graph it, and then draw the tangent line on top, then you can step back and see what's the slope of that line I just drew. You can estimate the slope of that line. Does that make sense? Yeah. All right, maybe. So parts of this are very old news. We all know what slopes of lines are. Parts of this are stupid, brand new, right? So it's really weird when those 2 things happen at the same time. But if you graph by hand the points that they give you, plot them and then connect them, and then draw in the tangent line on top. So when you graph the points, what would this look like? Looks to be a negative slope, right? So it might even, I don't think it's quite linear. Let's see. Every 5 is 200, 200, 100. All right, so it looks to be something like this maybe, very roughly. Is that cool? All right, that's my best estimate. And they're talking about the point at P, and what's point P? 15, 250. So that's right in the middle of everything. So you would draw in the tangent line as best you can, and that's an estimate. That's just an estimate that you're doing. And then you got a line. Then you just see what the slope of that line is. That's how you estimate it graphically if you graph it by hand. I like it. Will you be correct? No, it's an estimate. Jeez, give me a break, right? Cool. It's all by hand, so it's not going to be perfect. And then eventually we're going to learn how to figure out exactly what the hell that thing is. Yeah. All right. So that's number 1. All right. That's quite a good way to start off some homework. Yes? 6. Okay, good. So another part of this section is about velocity, but what is slope in general? So let's say I had years versus value of car. What would that graph look like? Yeah, and it would actually be it would actually be like that, almost, right? I mean, the minute you drive it off the lot, oh, it's 1,000 less than it was worth a second ago. No, maybe not that bad, but right? I mean, it's basically what it is. You guys kind of with me?
Yes.
So the slope of this at any point would be what units? What would the units of a slope be? You could do it. Okay, what's slope? What's slope? Change of y over change of x. And what's the y in? Dollars, right? And what's the x in? So a slope would be dollars per year, which is a rate of change, right? So slope is rate of change of whatever the y-axis is. If the x-axis is in time, the x-axis could be almost anything. X-axis could be in distance, so it could be the amount of sweat, and this would be the distance hiked. You guys with me? So every now and then you just stop and there's a lot of sweat. Stop a little bit. Good Lord, it's hot out here. What the hell? Right? You've ever gone hiking in Death Valley? Like, one day we were hiking in Death Valley when it was like 112 degrees, and the next day we were throwing snowballs at each other. And you said, where the hell were we? At least I don't know where the hell we were. Screw it. I can't remember. It's too long. I gotta take my ginkgo biloba. No, helps remember. So distance hike versus amount of sweat on your, let's say in cubic centimeters. You got your little, that's good. So if I go so many feet and then I can stop, what would the slope be? Cubic centimeters per foot. It's a rate of change of amount of sweat based on how far you go. It's a rate of change. That's the whole idea of slope, right? So that's why some of these problems are going to be about velocity, because of what is velocity? What is speed? It's a rate of change of distance, right? Position over time. So it is a slope of a position function. So if I had my, if I plotted my, going up a mountain, I plotted my position in meters versus the time, then the slope of it, so here I am, I'm going really fast at first, and then I'm like, oh shit, I'm getting tired. Right? So the slope would be my velocity, would be how quickly I'm moving. So if it just flatlines, it means I laid down for a while. Or I stopped and I ate, or I died. Right? Or just another person on Mount Everest. It's really morbid. I'm never going to do that. It's horrible. Alright. So let's actually do this question. I like it. So whoever asks this is probably like, can you just answer the question? If a rock is thrown upward on the planet Mars with a velocity of 10 meters per second, its height in meters t seconds later is given by this. Now, anybody know, you should probably know this, but on Mars, is the gravity more or less than Earth?
Less.
Less. And this number on Earth, anybody know what that number would be on Earth? Beautiful, 9.8. That's related to the acceleration of gravity in meters per second squared. Right? How much of that do you have to know what I just said to do this problem? None. But it's good to know. Find the average velocity for the time period beginning... No, Jeff, you start at A. There you go. Beginning at t equal 2 and lasting each of these things. So like part 1 says lasting 0.5 seconds. So remember what I told you. If they ask you to find the slope of the tangent line, or they ask you to find the velocity, which is the same damn thing as saying the slope of the tangent line, they mean the same thing. Is that cool? Because slope is a rate of change, and so is velocity. If you can get the 2 points, you can get the slope. So what are my 2 points on this first problem? So I want to start at what time value? 2 seconds. And then I want to know what's the average velocity starting then, and then 0.5 seconds later. What's the average velocity over that interval?
I thought it was 1 and 2. 2.5.
What's happening?
The points. I thought it was 1 and 2.
Oh, I'm looking at number 5. That's my bad. Number 6, they're like the same problem almost. Oh, okay. All right. So So that was number 5. Number 6 is actually a little more direct. Number 6 is a lot better. Number 6 just says, what's the average velocity over that interval? So that's even better. So this is the interval for time from 1 second to 2 seconds. So what are my 2 points then? 1 something and 2 something, right? Because that's not a point. That's an interval for t. That's my x-axis variable. What's my y for this? What's my output? What's my position for that? So I'm on Mars. I have thrown a rock up at 10 meters per second. So many seconds later, I know where it is according to this equation. And of course it makes sense because it's a down parabola and it should follow that kind of a shape, right? Or even if it goes straight up and straight back down, if I do it across time, it's going to look like a parabola. Cool. Of course, Mars is going to go a little higher than Earth. So at 1 second, where the hell is it? Yeah, 10 minus 1.86, so 8.14. At 2 seconds, where the hell is it? Something, I don't know.
5.1.
I thought it'd be somewhere around 13.
No, it's 13. I was looking at something else. I was doing the other question.
Where did I get the 8.14? Does everybody understand that? Some of you guys are looking at me like I'm insane.
Plugged it in.
Just plug the 1 in, right? And at 2 seconds, I'm just going to plug the 2 in. Should be about, okay, 12.56. Somewhere around 13 if you plug a 2 in there. And now all I got to do is find the slope, because the slope is always an average rate of change of whatever this is per whatever this is. And that's exactly what we're talking about right here. Let me just stop there for a second. Is that decent? You might never have said it like that, but that's truly what it is. And when we find the slope of a tangent line, if it's position versus time, that's going to be a velocity. That's how quickly my position is changing. That's how fast I'm going. So, just find the slope then. 12.56 minus 8.14 divided by 2 minus 1. Yay. So the average velocity from 1 second to 2 seconds is 4.42. 4.42 what?
Meters per second.
Yeah, meters per second. Cool. So don't forget units. This will be very much like science class, especially when you give you units in a problem, you better use units in your answer. Or I'm going to be a real dork and say light years per hour or something stupid. Question mark. Corn dogs per minute? You know, I'll be a real dork. Don't make me do that. I'm dorky enough as it is. So that's the same thing as part 1, 2, 3. They just make the interval. What are they doing? Like the next intervals are 1. Where'd it go, Jeff? 1.5, 1, 1.1. What's their goal here? What does it look like they're trying to figure out? Yes. What about 1?
The tangent line.
They want to know the slope of the tangent line. They want to know the velocity at 1 second. And that kind of doesn't make physical sense. So we call it the instantaneous velocity. Let me say that again. So this would be just an average velocity. That's like any normal average velocity over this interval. But if I want the velocity, bam, right at time 1, that's instantaneous velocity. And that requires the ideas of calculus to figure out. So this would be, so I'm trying to get the velocity at t equal 1. That's why I keep getting closer and closer. That's like making h go to 0. Bring my other point in closer so I can see what the slope is right there. Yes,
So I'm only approaching it from one side. Right?
I know, exactly. That's fine. That's good enough for that. That's. I don't think they actually ask you.
That's why I was confused.
Oh yeah. So in part B, they do ask you. The nice thing is I know what this thing looks like, and I know that it exists on both sides.
Right.
In general, you do have to come from both sides to figure out what the limit's going to be, right? But on this problem, it's a nice continuous function. It's a parabola, so I really can just come from one side. All right. And think about it. If and there's a whole section on continuity in section 2.5, but I will have certain words just come out that relate to things we're going to talk about later. You know about the idea of continuous. This has come up a couple times. Like polynomials are continuous. And the most basic definition of continuous is I can draw it without lifting my whatever is, my marker in this case, right? That's not good enough for us. We're going to come up with a much better definition of it, but that works for now. So if I find the limit as I come from above at this point is something, it's going to be the same thing as below because it's continuous. They got to agree. The only way they could disagree is if there was a break, right? Or there was some kind of infinite asymptote. But that's not going to work with a continuous function. How are we doing there? So it's a really good point. You normally do have to come from both sides, but it's a really nice function. Polynomials are the nicest functions ever, right? They'll be there for you. Okay. So what's hard for me right now, whenever I teach this, I always forget how weird this is for me, because there's so many different ways to look at the same problem, right? But there are fundamental ideas here. There's the idea of limit. The idea of limit is itself its own thing, like I tried to say yesterday. Then there's the idea of the slope of the tangent line that uses limits to help it out. Because it's all about what does it look like it's doing as it's getting closer, and that's what limits are for. We go, oh, limits, I can use those to help me see what that's doing. Right? Okay, maybe. But right now, fundamentally, these problems are on the level of algebra. It's just the terminology and how they present it that makes it look harder. But that's just finding a slope between 2 points. That's easy. Anything else from that?
We have one from 2.2.
Sure.
46.
Let's see if I have talked about it yet. Okay, we'll do that here in a minute. Well, and that one, well, yeah, let's hold off on that one. We could talk about it right now, but let me remind you about that here in a minute. All right, so anything else? So section 2.1 is all about specifically slopes of lines, right? And using either making tables and seeing what the pattern, what does it look like it's going to, right? Or estimating it from graphs, estimating what the slope is. Section 2.2 takes a step back and says, let's look at limits in general. How do limits work, period? Because we're going to use them to figure these things, these slopes out. And how do limits work? All right. So let me give you a few, and instead of me trying to graph various things and you guys going insane with my horrid lack of artistic ability, let me steal some from the book here. Oh, there it is. And then I got a little handout that I want you guys to work on your own. The problem people have with what we're about to get into is related to a problem that people have in pre-calculus, which is, let me see if I can remember. So in pre-calc, you talked about things like on what intervals is a function increasing, decreasing, right? Does that sound familiar? So let me see if I can make something real quick, a little quick example. So say my function was like that. Sure, why not? Funky little dude. Don't worry about that yet. So what I would always get is somebody would say it's increasing on the interval from -1 to 3. And actually I try to argue with them that you shouldn't even put parentheses, you have to put parentheses on there because at -1 I have no idea what it's doing. What's wrong with what I just did? Do you see what? And if you're like, there's nothing wrong with what you just did. All right, let's work through this because there is something wrong with what I just did.
The interval doesn't increase all through the entire thing.
But do you see why they put what they did?
Yes.
Because this is 3, isn't it? But the question is all about on what interval of x is it increasing, right? So it's not they don't even say that, but it's got to be part of what's understood. Where is it doing something is always the x-axis. What is it doing there is always the y-axis. So on what interval is increasing is from -1 to 0, right? This is what I was trying to draw anyway. Pretend like that's what it is. So, same kind of thing happens with limits. Because you've got to look from the below and from above, but your brain is all about, well, what's y doing at the same time? So you got to be, it's the same kind of mistakes that are made. So let me show you what the hell I'm talking about. Yes, please do, Jeff. Where's a decent problem? Let's start small. No crap. What was that? Go away. Return. Save and exit. Okay, good. Alright. Can somebody shut one of those lights off? Yes, good. Alright, sweet. Alright. And here, you guys should look this way. Alright, let's see what you think about this. So we have already talked about the what the symbol LIM means. We've talked about even. We've talked about. Have we done about the negative and the plus yet? I don't think we've done that. No. But what do you think that does mean? We've talked about the fact, like you brought up earlier, you've got to look from both directions. So that's the way we've decided to mean. Like part A says, what does the function output doing as the inputs approach 2 from below, from the left? You guys with me? And then part B is really the same exact question, except you're letting it go to 2 from above. So do you start to see what I mean about the mistake people make? So as I approach 2, so here's 2. As I approach 2, that's what the x's are doing. What does it look like my outputs are doing?
3.
It looks like they're approaching 3. All right, good. But and that's pretty straightforward, really. But people always find a way to look at the wrong place and to think about it incorrectly. It does not matter what this thing, it can be going insane. My x's are nice. My x's are just, I'm going this way. And then your y's can be doing all kinds of weird shit. But it's like, is it going somewhere as your x's are approaching something? Are your outputs approaching something? Cool. What about from above? Yeah, if I go to 2 from above, what are my outputs doing? They're approaching 1. So if I ask you, in fact, does it ask you? Yes, it does ask. If I ask you what's the limit as x goes to 2, period,
Doesn't exist.
does not exist. Because you couldn't say, it's not 1, it's not 3. They have to agree for there to be a limit to exist. Now, what is f of 2?
3.
Yeah, f of 2 is 3. Did they ask you that? Oh, look at that. Did that matter at all in the first 3 questions? It didn't matter worth shit. Because the whole idea of a limit is it never gets to 2. It has no idea what's actually happening at 2. And it can't tell you that. All it can tell you is it looks like it's going to do this. Right? Alright, I like it. I like it. And so now, what about part E? They didn't build up to it. They just...
4.
Yeah, as x approaches 4 from both directions. So when you don't see a minus or a plus, in order for it to exist, it's got to be going to the same place. But the question that was asked earlier was a good one, but it had a nice function. It was parabola. It was so I knew it was going to go to the same place from both sides. But here I got this funky ass thing, but thankfully they are both going to 4. But what is f of 4? Undefined, right? Because there is an open circle there. It's undefined. So you see how the function value out of x value has nothing to do with what the limit is at that value. Nothing. Right? And let me just get a little ahead of myself. Would you say that this is continuous through that point? No. Of course not, because you got to pick your pencil up to make the little circle. Right? Or you can argue, no, there's an empty hole there. You got to pick your pencil up to keep going. Are you with me? There's a hole there. You can't just keep going through it. Right? So in order for this to be continuous, think about this. Can you come up with a definition? This is almost continuous, except f of 4 is not defined. But even worse, what if f of 4, what if I put a circle right there? Now it's defined. Is it continuous? No. So not only does f of 4 have to exist, it has to be the same as... How would I make this continuous? Put a closed circle where? There. So the function value has to be the same as the limit. If the limit is the same as what it actually does, it's continuous. And to tell you honestly, we just did section 2.5. Not really. That's the big piece of section 2.5 is the definition of continuity. So I don't have to lift my pen up. It's fine. But a little more technically, at every point, the limit must be the same as what the function value is there. If you think about it, that makes that would be a continuous function. It looks like it's going somewhere, and it gets there. Hey, all right, yay. All right, maybe. Yes, sir.
The limit where it's approaching to from both sides, you would say...
Officially, the answer there, don't say undefined. You'd say does not exist.
Okay.
Good. I like it. Yes, sir.
Teachers don't like D&E. Are you okay with D&E?
Of course I am. They want you to write does not exist. This is math. What do we do in math? Try to make everything very efficient and concise. So if, I almost have to say they're not quite math teachers. I didn't say that. They have to be all over D and E. Now, you say D and D, that would, I don't know. Depends on other things. All right, so let's see. Let's do one more together that's got some weirdness to it. The sucky thing about this is it's in two parts here, but we'll survive. Well, maybe I'll do this one. I'll do this one, and then I'll talk about the other one. All right. So real quick. Now this introduces the idea that the answer could be some kind of infinity, right? So what's the limit as x goes to -7? Why? Now let me ask you this. Do they ask you about 6, right? Where's the 6? There. Let's go to, screw it. I'm going to ask you a question they don't ask you about. What's the limit as x goes to 6?
Does not exist.
Beautiful, because what's the limit as it comes from below?
Negative infinity.
Negative infinity. What's the limit as it comes from above?
Positive.
So of course the limit itself does not exist because it doesn't agree. Just like the problem we just did earlier, they were in two different places. They didn't agree. So here, this is the most different you could be. Right? This is the biggest disagreement that can be had on a graph. Alright? Alright. And then the other questions are pretty straightforward. Limit as x goes to -3. Good, because they both agree. They're both going to positive infinity. Limit as x goes to 0. Same thing. So here's the weird shit. Look at that. That looks like a seismograph or a lie detector thing, right? Polygraph, that's the word for it, if you want to use words. Or one word instead of many. Where am I at? Alright. So, this looks like, how the hell would this happen? But I don't know, I think I said this in my pre-calc class. I don't think I'll ever say it as well as I did then. But sine, of course, goes up and down forever, right? So what this is doing is, it actually took infinity and put it here. So this is like a sine graph. It's doing all of its oscillations, but it's getting it done right here. And that really can blow your brain. You can go, what? But a very simple way to have that happen is, normally you have to let this go to infinity to have something like, but what would this, what do I have to go to see, if I graph this, sine of 1 over x, it'll look like that around 0. Do you guys kind of follow what I'm saying? So actually, this is neat. The way I said in my pre-calc class is, you're God, and you said, I don't want infinity to happen, and I want infinity to happen right here. Because I'm freaking God. Anyway, like, all right, God, whatever. So it goes through all of its oscillations, all of its infinite oscillations right there. But that's not the point. I just want to explain what's going on here, that this could actually happen in a function. That's that simple to make it happen.
You're basically doing the transformation, right?
Yes, it's a weird transformation because it's an internal flip. Yeah. Yes, but so you are actually repositioning where infinity is, which is kind of a phrase you didn't think existed. Well, let's see. What do they ask us about here? You can see it right there. Limit as x goes to 0 from below. That's a nice normal question. What's the limit as x goes to 0? Yeah, what's the limit? Yeah, I think so. That'll give us the scale there. That's kind of evil. What's the limit as x goes to 0 from above? -1. So the limit as x goes to 0 is does not exist, or D and E. Cool. So what's the limit as x goes to 5 from above?
infinity?
No, as x goes to 5 from above is 3. Now here's the weird shit. In fact, it's the same question. This question is the exact same question, and it's too bad. The exact same question as this. What's the limit as x goes to infinity of sine x? If you don't think at all about it, you just go infinity. But of course, sine is always going from -1 to 1. So what's the limit as x goes to infinity? Does not exist. In a way, almost the same reason that if it's like this, it does not exist, right? Because they don't agree from both directions. This is almost the other way. It does not exist because it's always oscillating forever. It never settles on a value. It's always oscillating, right? And the weird thing about infinity is you can never get to it. So that's why this whole idea of infinite limits have their own section. But I figured we could talk about it because it's really just horizontal asymptotes, right? Letting x get really big. You guys still with me? All right, good. You're all looking in my direction. It's a good thing. But this is a little weird because I can never get there, but sine is just constantly oscillating. In order for there to be a limit, it's got to eventually agree to get closer and closer to something, right? For there to be a limit in infinity. This never agrees to do that. It's just always this. So this puts that idea so that you can see it. So what's the limit as x goes to 5 from below does not exist for the exact same reason this does not exist. It never agrees. It is always going up and down. So you can think about it as like it's going really kind of slow and then it speeds up and then it speeds up and then it speeds up. So it's getting infinitely fast the closer it gets to 5. Holy shit. All right, so that's just lots of weird shit can happen in math. Some of them actually have physical interpretations. That's right. Okay. So what I want you to do, I think you're ready for this. You're definitely ready for this. This is relative to what we just did. This is easy. So you can work on this alone or together. This should be, well, we'll see. I don't want to say too much. I don't want you to feel bad if you don't know what the hell's going on. If you don't know what the hell's going on, get help from people around you or call me over. This is not a quiz, by the way. I don't do pop quizzes. You don't have to show this to me ever. You can make a paper airplane out of it. Now somebody will do that. You could have a paper airplane contest. Origami. Anybody know origami? No, first do the problems, then you can do whatever you want to do with it. What's that? I don't know origami. You make me a crane? All right. And I want your crane. When you make the crane, I want this to be its eye.
I'm only happy.
I got to increase the challenge for you, right? Oh. Wait. Whoa. That was really nice on this.
The difference in the terms between undefined and does not exist. So you wouldn't say that 2 does not exist? You would say it's undefined? Or what would you say?
How do you mean? Oh, at 2.
Like if you were approaching it from both sides.
2?
Yeah,
Or
one.
one doesn't exist, the value is going to be. Like at point, or at x equals 5, that's an undefined. Or
The function is not defined at x equal to 5. The limit at 1 does not exist.
Okay.
You see the difference? So I say function. A function might not be defined for a certain x value, but a limit does not exist.
Period.
At a certain
Okay.
as it approaches a certain x value.
Okay.
Cool. I like it. That's actually defined. And -4 is not defined. gonna take some getting used to. Tuesdays and Thursdays, this class is over. Like it feels like it just started.
50 minutes ago.
Yeah.
Could we answer 46 before we go?
Oh yeah. Remind me.
For this, is that supposed to be?
Oh, did I ask? Oh no. Positive 6 from below, not negative 6. That's right. Yeah, you see it, you got negatives in weird places now, yeah. I got negatives in weird places.
So we run over 2.1 and this is 2.2.
This is 2.2. Yeah.
I already did 2. We did 2.
And 2.3 will be relatively quick. 2.4 is going to be the section that people really love, like algebra students and word problems.
Oh yeah.
Some teachers don't even do 2.4 in their hours.
At negative.
Oh, now the idea of right next to each other sounds simple, but in mathematics, that's a market. That is limiting process in itself. So that's a whole other conversation. And it's possible for that.
Both sides. Now this
It's
one
not
is 2.
easy to do.
Because it's the limit. Like if you were to ask what this function was, then that would be an algebra. But you're just asking
Yeah, so
what
if
it
you
looks
have
like.
a whole region,
It's not
basically
actually
closed.
going like this. It's saying
You have a whole region that's missing. You just made it really small for what you said. Then I can't even talk about the limit of anything in that region. So I couldn't really talk about the limit of either of those two specific points because I can't even right next to it. That's the line, right? Yeah, but you're right. It's a little above. All right, guys. This is definitely you get it or you don't kind of situation, right? How we doing? Are we all done? All right. Let's see. All right, here we go. You ready? This first one says, and this is where you can ask me if the printer doesn't, this is x goes to -4 from below, right? This is just different terminology, different symbols, but now we know what they mean. So as I go to -4 from below, of course the limit is 2. The outputs are approaching 2. From above, it's also, so in general, it's 2. Cool. So that's nice. So anytime you have that and there's a circle connecting them, then all 3 of those questions would be the same answer. Now, what is f to the -4? Undefined. Kick-ins the ass. I like it. Not just because that's an open circle, but because there's no closed circle anywhere that I can see. The limit as x goes to 1 from below. Good, is 4. And see, this is why people get confused. They say to 1 from below, and so they say, oh, I'm going to come up like on Jaws. I'm going to come up from below. Do you see what I'm saying? And some of you guys are like, I didn't even think about that, and now you've made me think about that. I'm sorry. But I'm just trying to make it not happen. So from below means as my x values increase to that value. What's my outputs doing? It's going to 4 From above, now that's this. That's from above. As far as x is concerned, that's from above. So what's it going to as it's approaching it from above? -2. That's the value. As I'm going to a 2 positive one from above, my outputs are going towards -2. Become a 2. Bam. That's even more so. So as I'm going to 1 period, good. D, N, E, completely acceptable to me because that's the right answer. And so what's f of 1 though?
4.
And this is where people, again, I like that a lot. You guys said that very confidently because you're right. They get confused. The limit not existing has nothing to do with what the function is doing at that point. Because the limit just didn't get there. But the function goes, oh, I'm all right. I'm right here. All right, you're 4. Good. All right, so what about this last bit? To 6 from below? 5 from 6 to 6 from above? 5 to 6? 5. Let me be careful. So as I go to 6, since a below and above agreed, that is what the limit is. That function is going to 5 no matter which direction you're going from, and that's what this symbol means when it's missing below or above. All right, this is not that rough yet, right? Notice how I said yet. And then what's f of 6? 2. Kick ass. So it's not undefined because it's open. It's actually defined somewhere right there. So let's do the problem. What was it? 46. Before we leave, so I don't forget. There we go. All right. I was waiting for that. Do you want it back? Who did that? No, I'm going to take somebody's eye out. That's all I need. Teacher was great, except that they took my eye out. All right, so your question was 46 and 2.
Theory of relativity question.
Oh, yeah. All right. So, guys, 46. In the theory of relativity, the mass of a particle with velocity v is this. And this, if you do any relativistic physics, some of you guys might have already done some or will do some. This is your correction factor. You see this in the expression when you go really, really fast, you actually get shorter. Right? So there's a problem in my quantum physics class where you have Otto is running really fast with his ladder, and his ladder is longer than his barn. How fast does he have to run so the ladder will fit in his barn? Because the length of the ladder shrinks when you go faster with it. It's not just anyway, screw it. That's enough about physics. So this question is saying, what happens as v goes to c from below? And of course, why can't you go to the speed of light from above?
Because there's nothing above this.
Because the speed of light is basically a speed limit, as far as most theories go. Right? So the limit. So how do I say this in limit terminology? Now, what happens as v goes to c from below? Well, I probably just put that underneath. So I want to go to c from below. I want to see what happens to the mass. Now, don't think too much about this. It's what you always try first with a limit question. Before you do any factoring or multiplying by conjugates, what you always do first is just plug the damn thing in. Right? I almost always have a question like this on a test. And people are factoring and doing all this weird shit. Plug a 2 in. 2 squared minus 4 is 0 over 4 is 0. I'm done. Next question, please. Do you guys understand what I'm saying? It's only at weird places. At nice places, 2 is nice. It's defined, it's beautiful, the limit is exactly what it's supposed to be. No problem. You guys. So if I try to plug a c in, what happens? What happens when I plug a c in?
It becomes 1.
Yeah, 1 minus 1.
0.
0. And every time I plug anything in, what's the sign of the bottom going to have to be? What is it, positive or negative? Positive. I'd like you to get a square root equaling a negative with nice real numbers, right? You guys still kind of with me? So if you get really close to C, this is getting really close to 1, this is getting really close to 0, this is becoming... Don't say undefined. Undefined is not good enough. Indeterminate is not correct because the top is whatever your mass is, not 0. Infinite. Positive infinity, right? This is a physical reality. Why can't we go the speed of light? Because the closer we get to the speed of light, the more massive we become. If we become more massive, what happens to me trying to continue moving that fast? I need more and more energy. So then I go a little faster. Now I'm even heavier. Oh, God. Sorry. I love that. There's a little old man going near the speed of light. I'm heavier now. Yeah, that just happened. All right. But see, this is a lot easier than it sounds, this problem, obviously, right? You let C go in. The important thing is which infinity. Don't say undefined
Positive infinity?
for over 0. In this case, it's positive infinity. So that means the mass approaches infinity. So if you wanted to go the speed of light, your mass is infinite. Which is why particles that travel at the speed of light
Have no mass.
are considered to be massless, right? Or at least their mass is negligible in some way. We'll stop there. All right. All right. Oh,